Can I start the talk?
Yeah, sure.
Thanks, Luca, for introducing me. Many thanks to the organizers for the opportunity to present my talk. I'm very honored to present it at this major satellite conference. We begin by introducing some requisite terminology. Any surjective mapping from the set of non-negative integers n onto a set S is called a numbering of S. If nu is a numbering of a countable family of sets, then nu is said to be computable or A-computable if the set of pairs xy, where x is an n and y is a nu of x, is CE or ACE respectively. If a family has a computable or A-computable numbering, we say that the family is computable or A-computable respectively. Such families are often called CE or ACE. When a set A is the nth jump of the empty set, the computable numberings are called sigma 0 n plus 1 computable. It is easy to see that sigma 0, 1 computable numberings are the same as the classically computable numberings. Next, we fix the standard notations for the classes of A-computable, sigma 0 n plus 2 computable, and computable numberings of given families. Gödel was one of the first to use computable numberings. He used computable numbering of formulas to embed the meta theory of arithmetic into arithmetic. Turing was the first to introduce universal numbering of the partial computable functions. And the basic concepts of numbering theory were formulated by Kolmogorov in the mid-50s. The first advances in the theory of numberings were obtained by Uspensky. He systematically studied the computable numberings of the family of all partially computable functions and found some of their applications in the computability theory. Rogers independently began a study of computable numberings of the family of all partially computable functions. He introduced a reducibility relation on the set of all computable numberings of this family, which defined a preorder on it. The factorization with respect to the equivalence relation induced by this preorder allows defining an upper Semilattices on the quotient set in a natural way. Subsequently, the Semilattices were called Rogers Semilattices. Then the theory of numberings emerged as an independent area of the computability theory. The most significant result in this area in those years were obtained by Burel, Maltsev, Yershov, Badaev, Goncharov, and others. Moreover, in addition to the numberings of the family of all partially computable functions, they began to consider the numberings of their subfamilies, as well as the numberings of families of C-sets, computable models, positive equivalences, and other constructive objects. Yershov's monograph contains a detailed bibliography of works in the theory of numberings of those years. In the mid-90s, Goncharov and Sorby introduced the concept of generalized computable numberings with respect to constructive languages that describe numbered families. This initiates the study of computable numberings in well-known hierarchies, such as the arithmetical and analytical hierarchies and the Yeshov hierarchy. Valuable results in this direction were obtained by Goncharov, Sorby, Badaev, Pazorov, Lemp, and others. The A-computable numberings, where A is an arbitrary oracle, were first independently studied in the 2014 paper by Badaev and Goncharov. And the first part of the talk is just devoted to the Reducibilities of A-computable families. For two numberings, nu0 and nu1 of the same set, we said that nu0 is reducible to nu1 if there is a computable function which for any x returns the number of the set nu0 of x in the numbering nu1. Two numberings are said to be equivalent if they are reducible to each other. The Reducibilities of an A-computable family is a quotient structure of its A-computable numberings with respect to equivalence of numberings. The operation of taking the supremum of two of its elements is induced by the direct sum of numberings. Note that even we consider the Reducibilities of A-computable families, the reducibility is still realized by computable functions. Next, we fix the standard notations for the Reducibilities of A-computable, sigma 0 n plus 2 computable, and classically computable families. Reducibilities can be viewed as an algebraic reflection of the algorithmic complexity of numbered families. Often, the more complex the oracle enumerating the family, the richer algebraic and model theoretic features each reducibility has. For example, consider the so-called effectively discrete families. Recall that a family is effectively discrete if there is a strongly computable sequence of finite sets such that each element of the family extends some element of the sequence, and each element of the sequence has a unique extension in the family. Maltsev proved that the reducibilities of any computable effectively discrete family is one element. On the other hand, Goncharov and Sorby showed that the reducibilities of any non-trivial sigma 0 n plus 2 computable family is infinite. In addition, Badaev and Goncharov proved that if the sigma 0 n plus 2 computable family is infinite, then its reducibilities has infinitely many minimal elements. By the classical result of Laplace, the reducibilities of every finite family of C sets has the greatest element. But this is no longer necessarily true if we turn to finite families of AC sets. So Badaev and Goncharov proved that for a Turing-complete set A, the reducibilities of finite family of AC sets has the greatest element, if and only if the family contains the least element under inclusion. Lachlan also describes the types of local isomorphism of reducibilities of finite families of these sets. It should be said that the type of local isomorphism of an upper semilattice is defined as a collection of isomorphism types of its principal ideals. Using additionally the description of Lachlan semilattices found by Pazorov, it turned out that the type of local isomorphism of the Rogers semilattice of any finite family containing two sets comparable under inclusion coincide with the collection of the isomorphism types of all sigma 0 3 representable distributive upper semilattices with greatest and least elements. If all the elements of the family are not comparable under inclusion, then its Rogers semilattice is simply one element. Pazorov also proved that the type of local isomorphism of the Rogers semilattice of any finite family of sigma 0 n plus 2 sets containing two elements comparable under inclusion coincides with the collection of isomorphism types of sigma 0 n plus 4 representable distributive upper semilattices with least and greatest elements. And if all elements of the family are not comparable under inclusion, then the type of local isomorphism of its Rogers semilattice is given by sigma 0 n plus 3 representable distributive upper semilattices with greatest and least elements. We begin our study of the Rogers semilattices with the well-known Yushov's questions. The first one is, what are the possible cardinalities? And the second one is when they are lattices. Gutareski and Selivanov proved that the non-trivial Rogers semilattices of computable families are always infinite and are not lattices. The Yushov's questions for families of arithmetic sets were studied by Goncharov and Sorbe. So they proved that the Rogers semilattice of any infinite sigma 0 n plus 2 computable family contains an infinite subset in which any two elements form a minimal pair. This means that they have no common lower bounds. And if a non-trivial family of sigma 0 n plus 2 sets is finite, then its Rogers semilattice contains an ideal isomorphic to the upper semilattice of all CE m degrees. By the well-known Yushov's result, the last one is not a lattice. Thus, the Rogers semilattice of any non-trivial sigma 0 n plus 2 computable family is infinite and not a lattice. Now let's start studying the Yushov questions for the Rogers semilattices of A-computable families, where A is an arbitrary non-computable oracle. It turned out that if an A-computable family is infinite, then its Rogers semilattice again contains an infinite subset in which any two elements form a minimal pair. If a non-trivial A-computable family is finite, then firstly, its Rogers semilattice contains an ideal isomorphic to the ideal of m degrees of all A-computable sets. And secondly, this ideal is not a lattice. By the well-known Joko's result, each non-zero truth table degree contains an infinite set of m degrees. Therefore, the introduced ideals are infinite. Thus, again, the Rogers semilattice of any non-trivial A-computable family is infinite and not a lattice. Previous results have shown the similarity of the structures of the Rogers semilattices of computable and non-computable families. So it is natural to ask whether the elementary theories of the classes of Rogers semilattices of all computable and non-computable families are equal. To solve this question, we need the definitions of distributive and weakly distributive semilattices. An upper semilattice is called distributive if each of its elements dominated by the supremum of some pair can be split under the pair. If we consider only non-trivial dominants, then we obtain the definition of weakly distributive semilattices. Note that any lattice is distributive if and only if it's distributive as the upper semilattice. It is well known that the Rogers semilattice of any finite family is distributive. On the other hand, Badaev, Goncharov, and Sorby proved that the Rogers semilattice of any sigma 0 n plus 2 computable family is not weakly distributive. This theorem can be generalized to any non-computable oracle A. As for computable families, the Rogers semilattices can be weakly distributive but not distributive. Thus, the second theory contains a sentence expressing the coincidence of the properties of distributivity and weak distributivity, while the first does not. Hence, these theories are different. One of the most intensively studied classes of A-computable numberings is the class of universal numberings. This is because the universal numberings contain information about all A-computable numberings of a given family. Recall that an A-computable numbering mu of a family S is universal if any computable numbering of S is reducible to nu. As we know from Lachlan's theorem, every finite family of C sets has a universal computable numbering. But if we switch to A-computable numberings, Lachlan's theorem is no longer true. Namely, Badaev and Goncharov proved that any finite family of AC sets, where A is a Turing-complete set, has a universal A-computable numbering, if and only if the family has the least element under inclusion. They also asked whether the second theorem remains true if we replace the Turing-complete set with an arbitrary non-computable set. It turned out that for an arbitrary set A, the following conditions are equivalent. The first is that the Turing degree of A is IP-immune. The second is that the Badaev and Goncharov's theorem is also true for the oracle A. The latter is that simply exists a family of AC, a finite family of AC sets without universal A-computable numberings. A corollary of this theorem is that the Lachlan's theorem is true for oracles of hyperimmune 3 degrees. By the definition, universal numberings induce the greatest elements of the Rhodes Semilattices of the numbered families. Gutareski Ethereum provides conditions that imply the already mentioned infinity of non-trivial Rhodes Semilattices of computable families and the limitness of their greatest elements, if they exist. This means that for any element A strictly less than the greatest element C, there is an intermediate element B. Gutareski theorem itself says that for any elements A and C of the Rhodes Semilattices of a computable family, such that A is not greater than C, there exists an element B that is strictly greater than A, but again not greater than C. The question of limitness of the greatest elements of the Rhodes Semilattices for families of arithmetic sets was studied by Faizrakhmanov. He proved that the greatest element of the Rhodes Semilattice of any sigma 0 n plus 2 computable family is limit if either the family contains the least element under inclusion, or it is finite, or it is computable in the previous arithmetical level. Thus, we have the following questions. The first of them is whether Gutareski theorem holds for the Rhodes Semilattices of A-computable or at least sigma 0 n plus 2 computable families. And the second of them is what orders can be embedded over non-greatest elements of Rhodes Semilattices. In particular, whether the greatest elements of the Rhodes Semilattices of A-computable or at least sigma 0 n plus 2 computable family are limited. So let A and B be non-computable sets, and B is T reducible to A. We say that an A-computable numbering of family S is B universal if any A-computable numbering of S is reducible to it by some B computable function F. As the following theorem shows, any non-B-universal A-computable numbering is the greatest lower bound of two strictly greater A-computable numberings. As a corollary, we obtain that if A is a class of some non-B-universal numbering of a family S and an element C is not greater than A, then A and C satisfy the conclusion of Gutareski theorem. Indeed, as an element B, one can take one of the elements of a pair with proper infimum A. Now we give one more sufficient condition for the truth of Gutareski theorem for A-computable families. It uses the notion of non-splittable numbering. We say that numbering gamma is non-splittable if it is not equivalent to any direct sum of strictly less numberings of subsets of numbered set. It is known from the papers of Selovanov, Badaev, and Goncharov that if A is a Turing-complete set, that any universal A-computable numbering is non-splittable. Now we fix some non-splittable A-computable numbering gamma and its equivalence class C. Let A be an element of the Reducibilities of the same family. If A is high over some set B, gamma is B universal, and A is not greater than C, then A and C satisfy the conclusion of Gutareski Ethereum. Finally, let A be a Turing-complete set, and A is strictly less than C. Then A and C again satisfy the conclusion of Gutareski theorem. Indeed, choose an arbitrary non-computable low set B. If the numberings in the class A are not B universal, then Gutareski theorem is true by the first sufficient condition. If the numbering from the class A are B universal, then gamma is also B universal. Then Gutareski theorem true by the second sufficient condition, sin A is high over B. I'm remaining that B is low and non-computable. In particular, the greatest elements of the Rogers Semilattices of sigma 0 n plus 2 computable families are limit. Let's now switch to the minimal numberings. A numbering mu of a set S is said to be minimal if it is reducible to any numbering that is reducible to it. Minimal numberings are usually considered as dual objects to universal numberings. A numbering mu is called positive if its numbering equivalence is C and single valued, if its numbering equivalence coincide with the equality relation. It's easy to prove that any positive numbering and hence any single valued numbering is minimal. Every finite family of AC sets has the list up to equivalence A-computable numbering. Indeed, we can enumerate all the elements of a finite family using an initial segment of natural numbers and use the remaining naturals as numbers of one set. Therefore, the minimal numberings are usually studied for infinite families. In the theory of numberings, often, when it is known that a class of numberings is infinite, its effective infinity is checked. We say that a class C of numberings of an A-computable family is A effectively infinite if by any A-computable subclass of C, we can uniformly choose an index of A-computable numbering not equivalent to any numbering in the subclass. This definition is similar to the definition of productive sets, but instead of C subsets, computable subclasses of numberings are considered. For the families of all C sets, Sergei Goncharov, Alexander Yakhnis, and Vladimir Yakhnis proved that the classes of its single-valued, positive, and minimal numberings are effectively infinite. This theorem can be partially relativized, namely by direct relativization. We obtain that the class of single-valued numberings of the family of all AC sets is A effectively infinite for every oracle A. And since any positive numberings is empty set prime equivalent to some single-valued one, we obtain that the class of all positive numberings of the family of all sigma 0 n plus 1 sets is empty set and jump effectively infinite for each n. Since by the theorem of Badaev and Goncharov, every infinite sigma 0 n plus 2 computable family has infinitely many pairwise non-equivalent minimal sigma 0 n plus 2 computable numberings, the question of the empty set n plus 1 jump effective infinity of the class of minimal numberings can be considered for any infinite sigma 0 n plus 2 computable family, and not only for the family of all sigma 0 n plus 2 sets. This question was formulated by Badaev and Goncharov in the same paper. It turned out that even we take a high set A, the complement of its third jump will be one reducible to the index set of all minimal A-computable numberings of any infinite A-computable family. This partially resembles Michael's criterion of productivity, according to which a set is productive if and only if the complement of the creative set is one reducible to it. Using the ideas of the proof of this criterion as a corollary, we obtain the A effective infinity of the class of minimal numberings of any infinite A-computable family, where A is an arbitrary high set. In the second part of the talk, we study the upper similarities of all X-computable families. Let omega X be the class of all X-computable families. Since the union of two X-computable families is again A-computable, omega X form an upper similarities under inclusion, in which the family of all XC sets is the greatest element and the empty family is the least element. These Semilattices were introduced and first studied by Degtev in 1991. It is not hard to see that omega X is not a lattice. This follows from the fact that every X-computable subfamily of both families S0 and S1 has a proper X-computable extension in their intersection. Below, we will consider some properties of the Fréchet ideals of these Semilattices. Therefore, we note that their atoms are exactly one-element families. Thus, the Fréchet ideal of omega X is equal to the class of all finite families of XC sets. We begin our study of the structure omega X with its subclass of minuends. An X-computable family is said to be a minuend if by subtracting any X-computable family from it, we again obtain an X-computable family. It is not hard to see that the minuends are definable in omega X. Indeed, a family A is a minuend if and only if for any X-computable family B. There is an X-computable family C, which is in fact the difference between A and B, such that C is a subfamily of A. The unions of A with B and C with B are equal, and C does not intersect B. Degtev proved that the minions form an ideal in omega x, which is not a lattice. As it turned out, the class of all minions coincide with the class of all finite families of XC sets. Therefore, the second one and the Fréchet ideal are also definable in omega x. Let's see what happens if in the definition of minions we consider only subfamilies of A. Recall that numbering nu is precomplete if every partial computable function has a total computable extension by modular nu. By the well-known Yershov's result, a numbering is precomplete if and only if it will satisfy the recursion theorem with parameters for partially computable functions. Further, let S be a non-trivial family with a precomplete, universal, positive computable numbering. Such families can be found in Yershov's monograph. Then S has an infinite computable subfamily A, such that, firstly, subtracting from it any of its infinite computable subfamilies, we obtain a finite family. And secondly, subtracting any finite family of C sets from A, we again obtain a computable family. Thus, in the definition of minions, we cannot consider only the subfamilies. Note that the properties of the family A from the theorem are dual to the definition of maximal C sets. Indeed, the difference between the family A and any of its infinite computable subfamilies is finite. And the difference between any co-infinite C superset of the maximal set W and W itself is also finite. In addition, maximal C sets also define the coatoms in the quotient lattice E star of C sets by the ideal of finite sets. But as it turned out, the families from the last theorem do not define atoms of the quotient semilattice of omega by the Fréchet ideal. Moreover, for any X-computable family A, there is an X-computable family B contained in A with n, such that the difference between A and B is infinite. On the other hand, let S be a co-infinite X-computable family containing all finite sets. If the index set of S is X double prime computable, then there is an X-computable superfamily A of S, such that difference between any co-infinite computable family B containing A and A itself is finite. Thus, the quotient semilattice of omega x by the Fréchet ideal has no atoms but has coatoms. Now we consider a class of families dual to minions. An X-computable family is said to be a subtriad if subtracting it from an arbitrary X-computable family, we again obtain an X-computable family. As well as the minions, the subtriads are definable in omega x. Degtev proved a criterion for the subtractability of finite families of XC sets. Namely, a finite family of XC sets is a subtrahend, F and only F. It contains only finite sets. Using this criterion, we can get new definable classes in X. Thus, the X of all X-computable families that consist only of finite sets is definable in omega X. It is not hard to see that a family A is in the X, F and only F, any of its finite X-computable subfamilies is a subtrahend. Therefore, the family of all finite sets is also definable in omega X as a singleton. Note that this singleton is invariant under the automorphisms of omega X. But in the lattice of all C sets, there are no such non-trivial singletons, since each computable permutations defines its automorphism. Finally, consider the so-called weak minuends. An X-computable family is said to be a weak minuend if its intersection with any X-computable family is X-computable again. How can we describe the weak minuends? Degtev proved that every completely C family is a weak minuend. Recall that a family is called completely C if there exists a strongly computable sequence of finite sets such that this family is a family of all C extensions of elements of the sequence. It is not hard to see that the union of any weak minuend and a finite family of C sets is also weak minuend. So we have the following question: is every weak minuend almost equal to a completely C family? That's all. Thank you for attention.
Okay, so thanks a lot to the speaker. So are there questions, remarks? So we are not so many people, so you could probably speak directly if you. Okay. So I have a question myself, probably very naive. So really nice talk. I really like the overview of all these results. I was wondering whether there are two different Turing degrees that are indistinguishable with respect to the Rogers semilattices that they realize. So can there be AB such that for any single family S, such that S it is the Rogers, and you consider the Rogers semilattice of the A-computable numbering to S, then there will be an S prime family such that the B-computable numberings of this that form the Rogers semilattice, it is isomorphic to the one for S. So you see what I mean?
I know that if we consider sigma 0 n plus 2 compute any non-trivial sigma 0 n plus 2 computable family and any non-trivial sigma 0 n plus 4 computable family, then the Rogers semilattices are not isomorphic. That is Podzorov's result.
Okay.
So if A is, for instance, zero jump, and B is, for instance, zero third jump, they corresponding Rogers Semilattices, but are not isomorphic. But I think it is very interesting question. Are there two incomparable Turing degrees and non-trivial families such that their Rogers Semilattices of all A-computable and B-computable numberings are isomorphic? That is open question.
Okay, thanks for that. Okay, so any other questions?
Yeah, I have one. Can I? So Marat, thanks for the talk. If we consider families without universal numberings, can we have some description of these Rogers similarities? For example, it's isomorphic to some m degrees of some sort. For example, for sigma 0 n plus 2.
I think that still an open question, but it is maybe depend on the also open question on existence of minimal and strong minimal covers in the Rogers Semilattices of arithmetic sets. They maybe depend to each other.
Minimal covers, yeah. Because I think that Padzorov did something about this, something like m degrees of immune or I'm not sure. But
Yes, I don't remember these results exactly. Yes. I see. Padzorov used the structures of m degrees computable from some immune sets to describe initial segments of Rogers Semilattices of arithmetic, not all Semilattices.
So we cannot describe yet those. Okay, thank you.
Okay, so any other question?
Yes, okay, I have a question.
Okay, please.
So, as far as I understand, there's this nice distinction between hyperimmune degrees and hyperimmune free degrees, yes, in the number theoretical fashion, yes?
Yes,
Like
even for finite families.
Yes, yeah. So, are there like, what do you think? Are there like any other classes of degrees which can be also, in a sense, characterized via these kind of numbering theoretic tools? Any other like natural classes of Turing degrees?
I think one can be considered low and non-low degrees. I have one conjecture that if we take any low C sets, that we can construct an A-computable family without minimal A-computable numberings. That will give, if it is true, that will give us the elementary difference between Rogers Semilattices of A-computable families, where A is a non-computable oracle, and Rogers Semilattices of families of arithmetic sets, since each of them contains an infinitely many minimal computable numberings, as already mentioned.
Okay, thank you.
I think no-low, high oracles can be considered in the answer of your question.
Okay, thank you.
Okay, so other questions? Okay, so if not, we can thank the speaker again. I mean, you will not hear our applause. I mean, probably only mine. Okay, good.
Thanks so much again for attention.
Okay, so thanks a lot. And we have
Okay,
Yeah.
sorry.
yeah, I mean, it happens all the time. Okay, so it's time for our second speaker. Right, I mean, let me make this question anytime. I mean, Julia, is okay for you if we record it?
Sure.
Okay, great. So our next speaker is Julia Knight. All of you know Julia. She made fundamental contributions in computable model theory. And today she will speak about describing structures and classes of structures.
Well, thank you very much for including me in this really very interesting meeting. I certainly enjoyed Marat's talk. Okay, so here's the outline of the talk. I'll first talk about how we describe specific structures and talk about notions of Scott complexity, Scott sentences, and Scott rank. And then I'll talk about how we characterize classes of structures and connect it with Borel complexity. And then I'll talk about some classification problems and the notion of Borel embeddings and Borel cardinality. And I'll say a little bit about the sort of slippery notion of useful invariance for classes of structures. Okay, so the basic conventions are structures are countable with universe omega, and languages are countable, usually computable, which means we can effectively tell what's a symbol, and also we can tell whether it's a binary relation symbol or a unary function symbol or constant. And classes consist of structures for a fixed language, and they're closed under isomorphism, modulo that the universe is going to be omega. So they're closed under the action of S infinity. So for describing structures, countable structures, L omega 1 omega is the right sort of language. So there we allow countably, it's an infinitary language, and we allow countably infinite disjunctions and conjunctions, but only finite strings of quantifiers. So here are some sample formulas. There's a sentence that says of a real closed ordered field that it's Archimedean. For all x, x is less than 1, or x is less than 2, or x is less than 3, or x is less than 4, or ... And this is an infinite disjunction, the ors. The following formula says of an element in an abelian group that it has infinite order. So to say that, we'd have to say about x, this element, that x is not equal to 0, x plus x is not equal to 0, x plus x is not equal to 0. I'm using plus because it's an abelian group. So again, there's an infinite conjunction. So for L omega 1 omega, we don't have prenex normal form. We can't, in general, bring the quantifiers to the front the way we do for prenex normal form for finitary formulas. But there is a normal form. What we do is bring the negations inside. And when we do that, what we get is sort of alternations of infinite disjunction exists and possibly infinite conjunction for all. So I'll say a little bit more about complexity of the formulas. We base a notion of complexity of these formulas on the number of alternations of those two combinations. So a formula is sigma 0, it's also pi 0 if it's just finitary quantifier free. For a countable ordinal alpha, a formula is sigma alpha if it's a disjunction of formulas that start with exists and then have something that's pi beta for some beta less than alpha. And a formula is pi alpha if it has the dual form. So it's a conjunction of countable, of course, of formulas that start with a string of finite string of for all quantifiers, and then something that's sigma beta for some beta less than alpha. I'll use another term. I'll say a formula is d sigma alpha if it's the conjunction of something that's sigma alpha and something that's pi alpha. So it's really a difference of sigma alpha formulas, where the sigma alpha, the one that's negated, is we write pi alpha. Okay, so I'll say something about computable infinitary formulas. So these are particularly useful when we're thinking about complexity of structures and complexity of things that are defined. And the computable infinitary formulas are L omega 1 omega formulas in which the infinite disjunctions and conjunctions are over computably enumerable sets. And we'll classify these formulas as computable sigma alpha or computable pi alpha for computable ordinals alpha. We can, of course, relativize it. We can think about, an x sigma 3 or taking CE relative to x disjunctions. So let's look at the complexity of the sample formulas that I gave earlier. So the sentence saying of a real closed ordered field that it's Archimedean, that's pi 2. There's the for all out in front, no infinite conjunction, but we collapse that with there's the for all. And then we have an infinite disjunction. And we don't happen to have any exist quantifiers also, but this is an alternation of those two combinations. So it's pi 2. And it's computable pi 2 because, after all, that infinite disjunction is over a CE set. And the formula saying of an element in an abelian group that it has infinite order, that's pi 1. It says about x, that x is not 0 and x is, but it's a CE disjunct, CE conjunction of the formula saying that x plus x plus x plus x is not equal to 0. Okay, so for describing a specific structure, that was our first goal. And there's the important theorem of Scott, saying that for each structure, countable structure, of course, there's an L omega 1 omega sentence phi, which we now call a Scott sentence because of Scott, whose countable models are exactly the isomorphic copies of A. And I'll give a proof sketch because I want to say something about the complexity of a Scott sentence that just comes from Scott's proof. So what Scott did was first find a family of formulas that define the orbits under automorphisms of tuples in the given structure. So if we have formulas phi sub A defining the orbit of the tuple A for various A in the structure, then we get a Scott sentence by taking the conjunction of some formulas, really one for each tuple. So rho phi, rho empty set, says what did the one element extensions of the empty function look like, empty tuple look like? So that really, what do the single elements look like? And they say that each of them satisfies one of the formulas phi b, and all of the formulas phi b are satisfied. And then rho A for a tuple A says, for all tuples U that satisfy phi A, what do the one element extensions of that tuple look like? And what the formula says then, so if phi A holds of U, then for all Y that might extend U by one element, the uy has to satisfy one of the phi ABs. And also for all B in the structure, the formula phi uy is satisfied by some B, by some y. So if the formulas phi A that define these orbits of tuples, if those all turn out to be sigma alpha, then just looking at the form of what we're getting, this conjunction of things, each of which is pi alpha plus 1, that's then pi alpha plus 1. So we see that we would be getting a pi alpha plus 1 Scott sentence if we had the orbits of the tuples defined by sigma alpha formulas. Okay, so here's a sample Scott sentence just for the additive group of integers. It has a d sigma 2 Scott sentence. And in fact, it's computable d sigma 2 because the disjunction conjunctions that might be involved are over CE sets. So I'll just say what the Scott sentence says. So we're taking the conjunction of a pi 2 sentence that just gives the axioms for torsion-free abelian groups. And a further pi 2 sentence saying that for any pair, x and y, there's some z that generates both. So this is the infinitary part. So this is the pi 2 sentence. And then there's a sigma 2 sentence. To get the d sigma 2, we have a pi 2 and a conjunction with a sigma 2. And the sigma 2 sentence says that there's some x that's not divisible by any n, not divisible by any prime, we could say if we wanted. Okay, so that's how we could characterize the group, the additive group of integers up to isomorphism. For free groups, I'll say a little bit about the at least the complexity of the Scott sentences. So this is joint work of a large group of people, and we all really seriously worked on this, and it took us some time to learn enough to actually write down the Scott sentence. So it turns out that, again, there's a d sigma 2 Scott sentence. So in general, for the free group of rank n, there's a d sigma 2 Scott sentence. And this turns out to be optimal. We can't do any better than that. So to get this d sigma 2 Scott sentence, we used results of Nielsen. So this is why it took us a while to say that it was going to be computable d sigma 2. So what Nielsen did was characterize the tuples of words that could take a basis for the free group on n generators to another tuple that would also serve as a basis. So these, he called them primitive tuples of words. And he first showed that you get them by finitely many easily reversible steps. The steps, switch the order of the basis elements, or replace a basis element by its inverse, or replace one basis element by the result of multiplying it by another basis element. So these are primitive transformations, but the primitive tuples of words describe what happens, describe after finitely many of those. And these are exactly the tuples of words that take one basis to another. And Nielsen showed that this set of tuples of words is computable. Essentially, you make progress. You can show that you make progress, and so the tuples of words are bounded in length. Okay, so this is what we used to get the computable d sigma 2 Scott sentence, and showing that it was optimal, we used index set calculations. Some of them relativized. And McCoy and Walbaum, two of the authors on the original paper, showed that the free group F infinity on infinitely many generators has a computable pi 4 Scott sentence, and that this is optimal. And for that, what was important was to say, was to write formulas that characterize a part of a basis, a tuple that could be part of a basis. So I won't say more than that. But the proof of optimality was quite difficult. Again, it's index sets, but but with pi4 things, you're looking at 5 jumps. So there's some further results on finitely generated groups and their Scott sentences. And with a senior thesis student, Saraf, and then Ho got some more results, and Ross in her senior thesis, supervised by Karen Lang, showed that some other familiar kinds of finitely generated groups also have d sigma 2 Scott sentences. So abelian, dihedral, polycyclic, and some of the groups of interest to geometric group theorists, the Lamplighter group, the Baumslag, Solitar groups. So these all turn out to have d sigma 2 Scott sentences. And where the groups were computable, they had computable d sigma 2 Scott sentences. So based on the known examples, Ho and I had conjectured that all finitely generated groups have d sigma 2 Scott sentences, and that the computable ones have computable d sigma 2 Scott sentences. But this turned out not to be true. So Harrison, Trainer, and Ho showed that there is a computable finitely generated group with no d sigma 2 Scott sentence. And this is a delicate construction. And I think it's still open whether you could give a finitely presented group that has this feature. Let me say a little bit about what Harrison, Trainer, and Ho did. So they first, before getting the result for groups, they looked at finitely generated structures in general, and they said exactly when there is a d sigma 2 Scott sentence. There's always a sigma 3 Scott sentence, because you can just say, and for computable structures, there would always be a computable sigma 3 Scott sentence for the finitely generated ones. You just say there exists a tuple, it's going to be the generators, and then you say that it generates the whole thing, and you say what the thing it generates looks like in the give it sort of atomic diagram. So I said a finitely generated structure. Yeah, so what they showed is, we know that sometimes you can do better for these various finitely generated groups, familiar kinds. We could do better. We could get the d sigma 2. And when does that happen? So they said exactly. So a finitely generated structure has a d sigma 2 Scott sentence if and only if it's not self-reflexive, where that means what that means is that there's no substructure that's generated by a tuple B such that the existential formulas true of B in A are all true of B in this smaller structure, in this substructure. So to disprove the conjecture for groups, what they did was construct a computable finitely generated group that's self-reflexive. And they showed, and this is quite interesting, I think, they showed that you can't do that for fields. So every finitely generated field has a d sigma 2 Scott sentence. He'd shown that certain forms were not possible to be the Scott sentence of an infinite structure. And he'd shown something else really interesting. If you had a pi alpha plus 1 Scott sentence and also a sigma alpha plus 1 Scott sentence, then in fact there'd be a Scott sentence that was d sigma alpha, really sort of lower complexity. And this result, it was based on something of Doug Miller on separating sets for disjoint classes of disjoint pi alpha classes closed under isomorphism. Okay, so that Montalban had a more recent result saying, really looking at what Scott did and then getting an if and only if, getting the other half of what Scott did. So he showed that there's a pi alpha plus 1 Scott sentence if and only if the orbits of all tuples are defined by sigma alpha formulas. So Scott's proof already gave the one direction, but Montalban gave the other, giving the definitions of the orbits if you had the pi alpha plus 1 Scott sentence. And then Alvear and Greenberg and Harrison Trainer and Turetsky, they have some more precise results, very, very recent. And they have examples that really complete the description of all possible forms of optimal Scott sentences and connecting it to orbit complexity. So I won't state all of their results, but when can you get a sigma alpha Scott sentence? And what does that say about the orbits? That's the sort of thing that they're doing. And especially when you get to an ordinal like sigma omega 1 CK. So looking at Montalban's proof, Alvear and McCoy and I extracted some more information, did something effective, but only in one direction. In the other direction, you can't do. It's false. So if A has a computable pi alpha plus 1 Scott sentence, then the orbits are defined by computable sigma alpha formulas. So Montalban's proof involved a kind of Mackay consistency property, and that's what we're doing also. But it's a special kind. As a corollary of our result, we got a finitely generated group has a d sigma 2 Scott sentence if and only if for some generating tuple, the orbit is defined by a pi 1 formula. And that's if and only if for all generating tuples, the orbit is defined by a pi 1 formula. And this is not very hard once we had the sigma 2 defining formula. So let's turn to the second part of the talk, describing classes of structures. For a countable language L, mod L is the set of L structures with universe omega. And that's a nice topological space. In fact, it looks just like Cantor space. And we could identify it with Cantor space. And for simplicity, what I'm going to do to show you how that works is let L be a relational language. But this isn't a big change. If we had a binary function symbol, we could think of it as a ternary relation symbol. Okay, so let C be a new set of constants representing the natural numbers. And let alpha n be a list of the atomic sentences that say that some relation holds of a tuple of constants from C. And then we'll identify the structure A in mod L with the function that says which of these sentences are true. So we have a list of them. We can make it a computable list if our language is computable. And f of n is 1 if in the structure A, alpha n is true. Where I'm now identifying so these constants were identified with the natural numbers. There. Okay, so mod L looks just like Cantor space. That's a nice Polish space. And we have there's the usual topology, which is a metric. And we have Clopin sets in P, where P is a finite function from saying what are the yes, no for the first few natural numbers. And we look at the NP is the set of functions that agree with P on that finite set. And the Borel classes are the elements of the sigma algebra generated by the NPs. Okay, so in the Borel hierarchy, a Borel set is sigma 0 and pi 0 if it's a finite union of basic Clopin sets. And what that means is it's axiomatized by a finitary quantifier-free sentence with constants. And for a countable ordinal, alpha bigger than 0, B is sigma alpha if B is the union of a countable collection of sets, each of which is pi beta for some beta less than alpha. And B is pi alpha if it has the dual form, if it's a conjunction, if it's an intersection, countable intersection of sets, each of which is sigma beta for some beta less than alpha. So the effective Borel hierarchy is similar, except now the countable unions and disjunctions are over CE sets. And this effective Borel hierarchy runs, the levels are through the computable ordinals, alpha. So there's some nice results that connect L omega 1 omega with the Borel hierarchy. So Lopez Escobar showed that a class, now it's closed under isomorphism, of course, and it's a class in mod L. It's Borel if and only if it's axiomatized by a sentence of L omega 1 omega. And Vaught refined that, saying a class is sigma alpha in the Borel hierarchy, again, closed under isomorphism, if and only if it's axiomatized by a sigma alpha sentence. Vaught's proof involved Vaught transforms, which always seemed mysterious to me. But I had a senior thesis student who gave a slightly different proof. Well, it looked very different, except if you squinted, then it really looked the same. So Sugao met this student and saw the proof and sort of squinted at it with us to see what happened. But Michael Vandenboom, in his senior thesis showed a set in mod L is effective sigma alpha, if and only if it's axiomatized by a computable sigma alpha sentence. And relativizing this, you get Vaught's theorem, but Vandenboom's proof didn't use Vaught transforms. He imagined building a generic copy of a structure in mod L, and the forcing language, there was propositional with propositional variables representing atomic sentences that might be true in this copy we're building with constants. And there's a formula saying for a Borel class, formula in this forcing language for the Borel class that we're interested in, that this copy is in that Borel class. And of course that says the original was too, because it's closed under isomorphism. And the important thing is there are predicate formulas that define forcing of these propositional statements. And these accomplish exactly what the Vaught transforms did. So seeing Vandenboom's proof, I finally understood what the Vaught transforms were for, what they were. I understood them somehow. Okay, so let's take a look at Borel embeddings and Borel cardinality. And this is really the classification problems. So Friedman and Stanley defined 4 classes, possibly in different languages, K and K prime, a Borel embedding of K and K prime. It's a Borel function taking K to K prime, such that for a pair of structures in K, input structures, they're isomorphic if and only if their phi images are isomorphic. So this Borel function preserves isomorphism. And we'll write K less than or equal B, K prime, if there is such an embedding. We'll write less than, strict less than, if you have an embedding one way but not the other. And we write equivalence if there were embeddings both ways. So the Borel cardinality of K is its equivalence class under this Borel embedding partial ordering or pre-ordering. Okay, so let me describe a sample embedding. And the original result saying that it's an important result. It says that undirected graphs lie on top under Borel embeddings on classes in Mod L. And what it shows, what Lavrov showed, was that you could embed Mod L in undirected graphs. There's slightly different embeddings due to Marker and Nice and others. And I'm actually going to describe the one that's in Marker's basic model theory book. So first, let's take the case where L has just one binary relation symbol, and then Mod L is the class of directed graphs. So the embedding takes a directed graph to an undirected graph. And there's going to be a special point representing each point in the input directed graph, and a special point representing each ordered pair. And I can give you a picture that shows how the embedding actually works. So if we had, for example, just a directed graph that has 2 points with an arrow connecting A to A prime, the corresponding undirected graph that really codes it has 2 special points, BA and BA prime, representing A and A prime. And we indicate that they represent elements by connecting them to a triangle. And then we have 2 special points for the ordered pairs. There's one that represents A prime and another special point that represents A prime A. And for the one that represents the arrow, we'll make that part of a square. And because there's no arrow going the other way, we'll make that part of a pentagon. Well, I think you can see we can do that with more points, and we can code any graph we like. We can even do more with Mod L. We'd need more special points and more n-gons for the different relations, and to say yes, no for the different relations. We'd need more special points for the n-tuples, and we'd need more n-gons, saying about those whether we had whether they lay in this relation or not. To see that the embedding is one-to-one on isomorphism types, this one that we just looked at, we can note that there's a copy of the input structure defined in the output structure. And the definition just really uses finitary existential formulas. We have an existential formula saying you're connected to a triangle, that says you're a point. We have existential formulas saying that there's an arrow that says there exists a one-stop connection and a no-stop connection, and a square connected to a square. And we also have an existential formula saying there was no arrow, and there we would say there exists a pentagon. But we have existential formulas that describe this, this embedding, says how we could recover the input structure from the output structure. So there are classes on top, and I'll list them. And the results are due partly to Maltsev, partly to Meckler, partly to Friedman and Stanley themselves, partly to Marker. So, but altogether, they managed to show that the following classes all lie on top: undirected graphs, fields, 2-step nilpotent groups, real closed ordered fields, and there's a new result. This is maybe a month old, due to Paolini and Schelach that torsion-free abelian groups lie on top. I'll say more about that later. I'll say more about a few of these items later. The classes not on top, I'll give a few examples of classes not on top for different reasons. So the Q vector spaces, those are not on top because there are classes with uncountably many isomorphism types, and you can't map into a class and preserve isomorphism because there are only countably many isomorphism types. So subfields of the algebraic numbers, there the isomorphism relation is Borel. There are uncountably many of the structures, but the isomorphism relation is Borel here, and it's not for certain other classes like abelian P groups. For abelian P groups, again, it's not on top, but there's a subtler reason. It has to do with the kind of invariance that you can to describe abelian P groups. You need the Elm sequence plus something that says what's the dimension of the divisible part. And there are even sort of low-level Scott's methods graphs that describe an arbitrary family of sets. So let me say something about interpreting one structure in another. I already said in the example of an embedding that I gave, the input was definable in the output, but if it were still interpretable, so the elements are represented by equivalence classes, then still we could recover the input structure. So an interpretation of A and B is a sequence of formulas that define a set of tuples in B and some relations on that set of tuples corresponding to the basic relations on the structure A. And there's a congruence relation, twiddle, such that the quotient structure is isomorphic to A. And for familiar examples of interpretations that you've known for a long time, like natural numbers and integers, integers and natural numbers, this D is a set of tuples of a fixed arity. So Montalban has defined a more general kind of interpretation in which the D does not consist of tuples of fixed arity. But I think I won't maybe say more about that. I do want to mention though this, how do we recover? So if this D and the twiddle and the negation of the twiddle and the RI stars that correspond to the RIs and their complements, if those are all defined by computable sigma 1 formulas, then there's a Turing operator that takes copies of B to copies of A. And if we had uniform on a class, we could recover the input from the output that way. If we had definability by formulas of L omega 1 omega, then there would be a Borel operator that would take copies of B to copies of A. So let me turn back to the reason fields lie on top. So I guess in the Friedman-Stanley paper, there was an embedding of graphs in fields, which I won't describe, but Maltsev had defined an embedding of fields or even rings in groups. And I'd like to say something about that one. So Maltsev's embedding took each field to its Heisenberg group, which consists of matrices, 3x3 matrices with ones on the diagonal, zeros below, and then 3 other arbitrary field elements up above. And Maltsev gave finitary existential formulas that define a copy of the input in the input field in the output group with an arbitrary non-commuting pair as parameters. And there's a reasonably recent result due to a large group saying that we could get rid of the parameters. So they're finitary, and we could make it a finitary formulas. So they're finitary existential formulas like Maltsev's with no parameters that for all fields effectively interpret F in H of F in a way that we can recover it. See. So the Friedman-Stanley embedding of graphs in linear orderings, I'd like to say just a little about that. It's too complicated to absorb fully, but I want to show you a little bit about it so that you can see it's not easy to imagine how you might get an interpretation that would let you recover the input graph from the output ordering. So the embedding takes the graph and produces an ordering, and the ordering is going to be a it's a subordering of the set of finite tuples of rationals under lexicographic ordering. So let A and there's some preliminaries to define it. So let A and be an effective partition of the rationals into disjoint dense sets, and let T n be a list of the atomic types in the graphs, where T1 is the type of the empty set. I'm just putting it first. And the types for K tuples, there are finitely many of them. Those are listed before the types for K plus 1 tuples. Okay, so we have a nice omega type list of the atomic types. And now I can say what is L of G. So for graph G, and this is directed, let's say, so it's really just a binary relation. L of G is a subordering of Q to less than omega with the lexicographic ordering, and the elements are the finite sequences, finite tuples of rationals, R0, Q1, R1, Q2, so on, dot, 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 and then the last is a K, such that for some I less than N, for all I less than N, Ri is an element of A0. That was one of the dense sets. Rn is in A1, that's another of the dense sets. And for some tuple little a1 through an, satisfying one of these types, the ai is in capital A sub ai, and the k is a number less than m. So this graph, it ends up being a collection of finite discrete graphs, finite discrete orderings, put together, mashed together. And each of those finite discrete orderings, maximal discrete sets, represents a tuple from the input structure. But you don't ever see what is the extension, and you don't ever see the input binary relation. You don't really see that as a whole. You just see something about tuples from the graph. You can detect that one tuple extends another by looking at something, but you never really see the whole thing. Okay, so that's maybe all I'll say about what this looks like. But okay, so we actually managed to show that there isn't an interpretation. So this is with Alexandra Soskova and Stefan Vodov. So we show that there don't exist formulas of L omega 1 omega that for all graphs define an interpretation of G in L of G. And these were ordinary formulas of L omega 1 omega. Harrison, Trainer, and Montalban showed the same thing by a very different proof. and approximately the same time. So let me turn to effective embeddings. Kekris had suggested that my students and I consider effectivizing the notion of Borel embedding, and we did that. So all we did was just, instead of Borel function, we took a Turing operator. We also defined another notion based on enumeration operators, but this one, well, I think it's the better notion, because you can use tools from computability, guessing it at what's going to be true about an input structure and constructing the output structure. Okay, so there are examples of this. In fact, the examples of Friedman, Stanley, and Leverov, and Meckler, and Maltsev, and Marker, these are all Turing computable embeddings. That's how they knew they were Borel. They were actually computable, Turing computable. There's a nice pullback theorem, pulling back statements in the language of the output structure to the language of the input structure. So if we have a Borel embedding or a Turing computable embedding, we can always somehow claim we've reduced the problem of describing the input structures to the problem of describing the output structures. And we say, well, okay, input structure, what's your corresponding output? And then how do we describe that? So we've sort of done it, but it'd be nicer if we could do that in the language of the input structure. So this theorem says you can. So in fact, it says if we have a Turing computable embedding, then for each computable infinitary sentence in the language of the output structures, we can find a sentence phi star in the language of the input structures, such that the input structure satisfies that phi star, if and only if the output structure satisfies phi. Then moreover, the complexities match. So if one is computable sigma alpha, so is the other. And the proof of this was forcing and definability of forcing again. We can use the pullback theorem to show non-existence of certain Turing computable embeddings, in particular for graphs in abelian P groups. And results of Safransky then let us extend that to show the non-existence of Borel embeddings. Friedman and Stanley had shown this. Although the proof isn't in their paper, you somehow extract it from some other papers. So for invariants, let me turn to this slippery, what are good invariants? What are nice invariants? So if we have a Borel embedding of one class and another, the embedding does reduce the classification problem for K, the problem of describing individual structures in K up to isomorphism, to that for K prime. And having the same Borel cardinality means essentially having the same invariance. So exactly what counts as useful, that's useful invariance. I'm thinking about sentences, somehow a way, or numbers, or some way to describe structures that seems helpful, more helpful than just, here's the structure. So for Q vector spaces, we give the dimension, and everybody sort of sees that as useful. Abelian P groups, the Elm sequence plus the dimension of the divisible part. That's more complicated, but I think most people accept that as useful. For Boolean algebras, Kettner gave some invariants that I think Camerlo and Gauss said, these are very complicated. And to me, they look like, here's the Boolean algebra. They don't really seem to help. Although Kettner did use them to prove some things. So I won't say they can't be used for anything, but. So let's turn to torsion-free abelian groups and say just a little. So the torsion-free abelian groups of rank n, this is the class of torsion-free abelian groups where there are n, well, the torsion-free abelian groups of rank n, they look like the subgroups of q to the n. And they're the ones that have z linearly independent elements, and they have dimension n. And there were bare invariants for rank 1. So for a group of rank 1, what do? You take a non-zero element and you say what divides it, which n divided or which prime powers divided. It's the same. And for different choices of A, you get slightly different sets, but the sets only differ finitely. And this was essentially the bare invariance. Up to finite difference, it's what divides one particular element. And most people accept Bare's invariance as useful. But there were invariants defined by Maltsev and Courage for n bigger than or equal to 2. And you can do it. You essentially just, for a group, you look at the a z independent n tuple, and for each z linear combination, you say which n divided. And the sets depend on the chosen tuple, of course. And there are transformations that would get you from one tuple to another, given by matrices. But these Maltsev and Courage invariants, as Hort and Thomas both report in their papers, Fuchs immediately dismissed these as no better than the group itself. And I think people don't really think of those as useful, although they're somewhat natural, and they're not complicated. The Scott sentences are not very complicated. Anyway, so Hort and Thomas showed that these torsion-free abelian groups become strictly more complicated to describe in the notion of Borel embeddings. That the rank 1, it's obvious that you can embed rank 1 and rank 2 and rank 2 and rank 3 and so on. But it's not so easy to see that you can't embed the other way. And that's what they showed. So this used quite a bit of descriptive set theory. So it used the Doherty Kekrich, oh, no, I'm blanking on it. Theorem saying that for a countable equivalence relation, it's embeddable in E0 if and only if it's hyperfinite. So they used that, and they used some other things. They eventually had to define a measure on the subgroups of rank n, and it was complicated what they did to get these results. So I'll mention one other result. Harrison, Trainer, and Ho showed that the class of torsion-free abelian groups of finite rank lies on top among classes of finitely generated structures. And I think that's an interesting result. So together with Turbo Ho and Russell Miller, we'd actually like to understand these torsion-free abelian groups better. We'd like to see if we can use any methods from computability to simplify, in any way what we do. And I guess we're looking at different kinds of generics. And we'd like to see if we'd like to see if we can do something, understand these results using some of our techniques, but we haven't succeeded. For the Paolini-Shelach embedding of graphs in torsion-free abelian groups, we'd like to try to see if it fails to correspond to a uniform interpretation. It looks to me a little bit like the Friedman-Stanley embedding of graphs in linear orderings. It's complicated, and I can't claim that I've understood it well enough. The outputs are rigid groups, and that's an interesting fact. but again, it feels to me as if you're seeing tuples, but not the whole thing. Anyway, I'll stop. Thank you very much.
Okay, so thanks a lot, Julia. And for the questions, maybe we can even try like that. You can just raise your hand, and I guess I can see all of you. So more or less, keep your hand up if you have any question, remark. Okay. So Sugao, please.
Hi, Julia. It's very nice hearing your talk again, and it's been a while since I last have any meeting with this group over here, so I really appreciate the opportunity. So I have a couple of questions. One is a technical question, which is, if you go back one slide over here, you mentioned the most recent result for about the finally generated, so what is it, torsion-free groups being on top. So you said a billion, but in the statement, it
Oh, no. Yes, I didn't mean a billion. Torsion, yeah. Yes, torsion-free abelian groups lie on top under, this is the Paulini-Shelach result.
Right. So
For the finitely generated, among finitely generated structures, was that what you were?
Yeah.
The
so
finitely generated torsion-free abelian groups lie on top just among finitely generated structures.
Okay. So that is, I've been connected with this topic for a while. So that is actually what we refer to as the E infinity, the universal countable equivalence relation. Is that right?
Yes.
Okay.
Yes.
So that is one question. The other question is a slightly off topic over here, because the most recently I run into a question which I thought that somebody must know the answer, but I couldn't find any reference. This is about a class of locally finite groups. As we know, locally finite means that any finite set in the group will generate a finite group subgroup. So
that's right. Yeah.
I don't know if anybody here knows whether the class of locally finite groups are on top, like is on top of this overall hierarchy. And this is just my curiosity. I haven't thought too much about it, but I happen to run into this. So I was wondering if you actually have seen any of that.
No, I haven't. Possibly someone else here knows.
Thank you.
But it's an interesting question. Yeah. Yeah, the finitely generated groups were important in some of the index calculations to structure that we were sort of building would be locally finite. But not, or finite.
That's right. Yeah, it's somewhat the opposite of what we have considered before.
Yeah, yeah.
Okay, so maybe other questions, remark? Maybe some of you know about the locally finite. So. Okay, so if not, I actually have a curiosity myself. So if I got correctly, Julia, you said that abelian P groups are on top under Borel reducibility, but not under Turing-computable embeddings.
Oh, no, the abelian P groups are not on top under Borel reducibility.
Okay.
And the reason they're not, essentially what Friedman and Stanley say in their paper is that the invariants for abelian P groups look like a sequence of ordinals. for graphs, you have a an infinite sequence of ordinals, where you could have an infinite family of sets for certain graphs.
Okay, so thanks for the clarification. So my curiosity was, what about continuous embeddings? So is it known whether there is a natural family of structures which is on top with Borel reducibility, but not if you ask the embeddings to be continuous?
Oh, yeah, I'm not sure. So the examples I know about that are Borel embeddable but not Turing embeddable are continuously embeddable. So things like the models of a particular completion of piano arithmetic, elementary first order theories, take some elementary first order theory that's a completion of PA and look at its models. You can sort of embed linear order but you can do it in a continuous way. So yes, I don't know. Just right off the bat.
Okay, so let's see someone else got any kind of question. Okay, perhaps not. Okay, so that was the last talk for this session, and we have the next session in 1 hour. So in any case, I think we probably leave this room open so that anyone can converse or whatever. Okay, so thanks a lot to everybody.